Hello everyone, welcome to the channel. So in this video, I'm going to show you the 4 decade of NDVI analysis using Landsat series in Google Earth Engine. So now let's get started. So the long-term monitoring of vegetation dynamics is crucial for understanding the ecosystem health, land use changes, and its impact on climate variability. So one of the most widely used indicator for vegetation analysis is the Normalized Difference Vegetation Index, which provides quantitative insights into the vegetation greenness, the density, and the photosynthetic activity. By using the satellite-based observation, the NDVI enables the researchers to track the temporal and spatial patterns of the vegetation changes across the multiple decades. So, the Landsat mission, initiated in 1972, provides one of the longest continuous records of the Earth observation at a medium spatial resolution of 30 meters. And its successive missions like Landsat 4 ranges from 1982 to 1993, and Landsat 5 from 1984 to 2013, and Landsat 7 in 1999 to present, and Landsat 8 from 2013 to present, and last is the Landsat 9 from 2021 to present, which offers a consistent framework for the multi-decadal environmental monitoring. Each satellite is equipped with a specific sensor such as the thematic mapper, an enhanced thematic mapper plus, an operational land imager, which captures the spectral reflectance data in the visible, near infrared, and the short wave infrared bands. These data are essential for computing the NDVI and analyzing the vegetation changes over time. So this analysis, we're going to implement a 40 years of NDVI trend analysis using Landsat archive within Earth Engine. So the workflow, we're going to integrate the surface reflectance product from the Landsat sensors to ensure a consistency across the decades. For the Landsat 7, both the LSC-on and the SLC-off periods are considered, with the gap filling methods applied to address the missing scanline data. And further, the NDVI is calculated separately for the 8 sensors. For example, Landsat 4, 5, and 7. The NDVI is derived from the red band and the near infrared band. And for Landsat 7, the LSC-off, the NDVI is corrected using the focal median filter for the scanline gap filling. And for Landsat 8 and Landsat 9, the OLI sensor, the NDVI computed from the red band and the near infrared band. So after the NDVI's computations, the image collection from different Landsat missions are merged into a continuous multi-decadal dataset spanning from 1982 to 2024. So a time series chart of mean NDVI value is generated to visualize the long-term vegetation trend, enabling the detection of greening and degradation or seasonal fluctuations within the defined study region. So in addition, a specific annual composite and examples of the gap-filled imageries are produced to demonstrate the census continuity and the data reliability. This analysis provides a comprehensive overview of the vegetation dynamics across the 4 decades at high temporal resolution. So the results is going to contribute to understanding the ecosystem response to climate variability, the land use changes, deforestation, and agricultural expansion and urbanization, and it serves as a baseline for a sustainable resource management and environmental planning. So now let me get back to Earth Engine. So to perform our NDVI analysis for the Landsat series image, first we have to define our region of interest. So the first step, I'm going to navigate to a farmland where I'm going to analyze the NDVI changes here. So for example, I have navigated to this particular study area. So you can able to see the farmland here more clearly and accurately. So here I'm going to select one of the study area here. So I'm going to select a study area over this particular farmlands here. So to create my study area, I'm going to navigate to this option called draw a rectangle. So once you did that, we're going to draw a rectangle over the study region. So you can able to see that. So here you can able to see I have already created a polygon here. Let me delete that. So now to create your study area, navigate to this option called draw a rectangle. So I'm going to click this and I'm going to draw a rectangle over this particular farmland here. So once you have drawn your farmland of your choice here, the next step, so in the top section, a new variable appears called geometry here. So I'm going to navigate to this variable called geometry, and in that I'm going to click this option called show generated code. And you can able to see this geometry contains a latitude and longitude of this particular study area. So I'm going to copy this latitude and longitude here. So using Ctrl C in my keyboard. And once you copied it, let me turn this off. And the next step, we're going to paste this latitude and longitude inside this variable called boundary points. So we're going to paste this latitude and longitude inside this variable called the boundary points here using Control V in my keyboard. So once you have pasted your latitude and longitude inside this variable called boundary points, in the next step we're going to convert this latitude and longitude into a polygon. So to convert this latitude and longitude into a polygon, we're going to define another variable called area of interest is equals to earth engine dot geometry dot polygon. So we're going to use this particular function to convert this latitude and longitude into a polygon. So and we're going to refer this particular variable name called boundary points, referring to this particular variable. So now it's going to convert this into a polygon. And the next step, to center this particular layer, we're going to mention map dot center object, and we're going to refer this variable name called area of interest, and with a suitable zoom level. And the next step, to add this layer, I'm going to mention map dot add layer area of interest, referring to this particular variable with the default visualization parameter, and we're going to output the layer name as study area. So once we created our region of interest, in the next step we're going to find our WRS path and WRS row. So the WRS refers to the worldwide reference system, is used to identify the path and row of each Landsat image, and the path is a descending orbit of the satellite, and each path is segmented into 119 rows from north to south, and the Landsat MSS sensor had a swath width of 180 kilometers, and the global coverage required is 251 paths. So now to find out the WRS path and WRS row for this study area, so we're gonna import our Landsat 8 imagery. So I'm gonna import my Landsat 8 imagery. So by defining this variable dataset equals to earth engine dot image collection Landsat LC-08 CO2 T1 top of the atmosphere, and we're gonna filter with this timeline here. So we're gonna mention dot filter date 2017 January 1 to 2017 December 31st. So the next step, we're going to filter it based on our region of interest using dot filter bound area of interest, referring to our study region. So now we're going to mention the print dataset in order to visualize the metadata property. So in the metadata property we have the WRS row and WRS path, which is the one we're required for now. So we have to find the WRS path and WRS row of the study area. So now let us visualize the WRS path and WRS row. So we're going to click this option called run, and now let us visualize the result in our console section. So we're going to navigate the image collection here, and here you can able to see this option called features. I'm going to click this option, and I'm going to select one of the satellite image. So we're going to select the third one here, and we're going to navigate to this option called properties, and in down we're going to find the WRS row and WRS path here. So we're going to go down here, and I'm going to find the WRS path and WRS row. So the WRS path is 39 and the WRS row is 30. So we're going to use this WRS path and row. So the WRS path for the study area is 39 and the WRS row for the study region is 30. So we're going to note it down here, 39 and 30. The path is 39 and the row is 30. So once we calculated the WRS path and row, so we have found the WRS path and row. So next we're going to perform the NDVI calculation functions for different sensors. So for example, these are the following satellite imageries we're going to use it for our analysis, starting with the USGS Landsat 4 Level 2 Collection 2. So the dataset availability is from 1982 to 1993, and the dataset provider is USGS, and the resolution is 30 meters. And similarly, the next Landsat imagery is Landsat 5. So the dataset availability is from 1984 to 2012, and similarly it is 30 meter resolution. And next is the Landsat 7. The dataset availability is from 1999 to 2024, and the dataset provider is USGS, and similar 30 meters. And next is Landsat 8, which is available from 2013 to 2025, and similarly it is 30 meter resolution. And last is the Landsat 9 image. So it is from 2021 to 2025. The dataset provider is USGS, and similarly it is 30 meters. So in our first step, we're going to perform the NDVI calculation functions for the different sensors, starting with the Landsat 4, 5, 7, 8 and 9. So let us perform our NDVI calculations, starting with the Landsat 4, 5 and 7. So with the SLC on period for Landsat 7. And first we're going to define a function called calculation NDVI. So cal NDVI TM ETM, referring to the image here. And inside this function we're going to define another variable called scaled bands equals to. So we're going to apply the scaling and offset factor. So let me show you that the scaling factor here. So you can able to see here the scale factor, it is 2.75 to the 10 to the power of minus 5. So it is a scale factor, and the offset factor is around minus 0.2, and it is similar for all the bands here. So let me get back to the Earth engine. So we're going to apply the scaling factor, so which is similar for the Landsat 4 and Landsat 5 and Landsat 7. So first we're going to define a variable called scaled band equals to image dot multiplying the scaling factor. Let me show you that. So this is scale factor, we are applying that 0.0000275, and the offset factor is dot add minus 0.2. So the next step we're going to perform the NDVI calculations. So for that we're going to define another variable called NDVI equals to the scaled bands, so referring to this particular variable, and we're going to apply the calculate the normalized difference. So we're going to apply the normalized difference to calculate the NDVI, that is normalized difference vegetation index. So we are applying this function dot normalized SRB4 comma SRB3. So it's going to represent the formula SRB4 minus SRB3 divided by SRB4 plus SRB3, and last we're going to rename as NDVI, and we're going to return this image NDVI with the system metadata property of this image along with the metadata properties. So we're going to mention return NDVI dot copy properties image dot property function. And similarly we're going to perform the similar actions similar for the Landsat 7 SLC-off period gap filling is applied. So let me explain about this Landsat 7 SLC-off period. So Landsat 7 SLC-off period gap filling. So the Landsat 7 was launched in April 1999 with enhanced thematic map of plus sensor functioned normally until May 31, 2003, when its scan line corrector, a mechanical device, was designed to compensate for the satellite's forward motion by shifting the scanner's mirror, and it's failed. So this failure resulted in the persistent edge-shaped data gaps, commonly referred to as a stripping, which account for approximately 22% of the missing data per scene. So despite these gaps, the remaining 78% of the data retains the high radiometric and geometric quality, making it still valuable for scientific applications when appropriately processed. So the NDVI analysis, in the NDVI analysis, these gaps can significantly distort the vegetation indices, particularly in time series studies, so which is necessitating a specialized gap filling approaches. So the common method including applying a focal median filter, which interpolates the missing pixel using valid values from the defined neighborhood. Example is the 10 pixels, and multi-data compositing that combines the multiple images from same seasonal or monthly windows to leverage an overlapping valid pixels from the adjacent scenes, and data fusion technique that integrates the information from other sensors like the Landsat 8 or MODIS acquired at similar times to reconstruct a complete and a continuous image. So we're going to apply this function called focal median function. So it smooths out the missing value by utilizing the nearby pixel values, while the bend function overlays the filtered image with the original NDVI image to preserve the valid data and only replace the missing or the gapped portions. Together these steps produce a gap-filled NDVI image that is suitable for the long-term vegetation monitoring. So an important advantage of this approach is that it preserves the continuity of the Landsat 7 archive even after 2003, ensuring that the multi-decadal NDVI trends can still be studied without a discontinuity. So it is also cost effective since the Landsat 7 continues to provide a useful imagery despite the SLC-off problem. So however, there is a certain limitation. The gap-filled pixels are only estimates rather than the original observations. So, and in the heterogeneous landscapes such as the urban area or the fragmented vegetation, the gap filling process may blur the fine spatial details. Furthermore, the accuracy of the results strongly depends on the quality of the neighboring pixels or on the availability of the complementary data source. So in the Landsat 7, LSC-off period refers to the data collected after May 31, 2003, when the image begins showing systematic missing strips due to the hardware failure. And in NDVI analysis, these gaps are corrected using the gap filling techniques such as the focal median filters or the compositing, thereby ensuring that the desired dataset remains useful for vegetation monitoring and the land cover studies. So let me get back to Earth Engine. So in order to solve this problem of the gap filling issues, we're gonna apply a function. So we're gonna perform Landsat along with we're gonna apply this focal median function, filter function. We're gonna apply that. So first we're gonna define a function called cal NDVI LSC-off image, and we're gonna create a variable called scale band equals to. We're going to apply the scaling and offset factor image dot multiply 0.0000275 and dot add the offset value minus 0.2, and inside we're going to perform the NDVI analysis in NDVI. So we're going to define a variable NDVI equals to the scaled bands dot normalized difference SRB4 comma SRB3, and we're going to rename as NDVI, which is similar to the one we performed above. And for the in case of this the gap issues, we're going to define another variable to apply the focal median filter. So we're going to define a variable gap fill equals to NDVI dot focal median. So here we apply this particular function called focal median, and the one here which refers to the radius of the kernel, and followed by the square which refers to the shape of the kernel, and the pixel here which refers to the unit for the radius, and last is the 10 which refers to the iteration. So the 10 this means that a filter is applied 10 times iteratively, so it can fill the larger gaps, especially for the Landsat 7 LSC-off. And in the next step we're going to define another variable called filled NDVI is equals to the gap fill dot blend. So the blend function here we are using. So the blend function basically it is a function which merges the two images together. For example, the gap fill where we applied the focal median filter, and we're gonna merge with NDVI, and last we're gonna rename as NDVI. And the next step we're gonna return the filled NDVI dot copy property. So it's gonna copy all the metadata of this particular imagery to this filled NDVI. And the next step, similarly, we're going to apply the scaling factor, and we're going to perform the normalized difference vegetation index for the Landsat 8 and Landsat 9. So to perform this scaling factor and normalized difference calculation for the Landsat 8 and Landsat 9, we're going to create a new function called calculate NDVI OLI image, referring to the image Landsat 8 and 9. And inside this function, we're going to mention a variable called scaled band equals to image dot multiply 0.0000275 dot add minus 0.2. So this is scaling factor, and this is the offset factor, which is similar for all Landsat imageries. And in the next variable, we're going to define a variable called NDVI is equals to scaled band, referring to this particular variable where we apply the scaling and offset factor, so which is need to be performed before performing any analysis. So we have to apply the scaling and offset factor. So we refer this scaled band dot normalized difference SRB5 comma SRB4, that is SRB5 minus SRB4 divided by SRB5 plus SRB4. And last we're going to rename as NDVI. And we're going to return this image as a return NDVI dot copy properties, referring to the image here, which represents we're going to copy all the metadata property of this Landsat 8 image 8 and 9 data to this image NDVI. And in the next step, we're going to show you now we have performed all the functions where we need to apply the scaling factors and calculate the normalized difference vegetation index, and we apply this for the focal mean filter for Landsat 7 SLC-off period. And now we're going to show you we're going to load this image. So for example, we're going to load the Landsat 4 imagery, which is available from 1982 to 1994. So to access the Landsat 4 imagery, we're going to define Earth Engine.image collection Landsat LT04 CO T1 L2. And the next step, we're going to select dot select SRB dot star, which is going to select all the bands of Landsat 4 imagery, and we're going to filter it based on specific timeline. So using dot filter date, and we're going to apply the filter based on specific timeline from 1982 to 1994, using dot filter date from 1982 to 1994. And next step, we're going to filter it based on a region of interest, that is dot filter bound area of interest, that is our study area. So this is our study region. And the next step, we're going to filter it based on the cloud cover lesser than 45%. So I'm going to mention the filter dot filter earth engine dot filter dot less than cloud cover 45. So we need a satellite imagery with a cloud contamination lesser than 45. And in the next step, we're going to filter it based on the WRS path and WRS row. So previously we have calculated the WRS path and WRS row for this particular study area. So which is WRS path is 29 and the row is 30, and we're going to mention this using dot filter earth engine dot filter dot equals to WRS path is equals to 39, and similarly we're going to mention dot filter earth engine dot filter dot equals to WRS row is equals to 30. And in the last step, we have to apply the scaling and offset factor for this particular Landsat 4 imagery. So for that, we have previously defined this particular function, that is dot map cal NDVI TM ETM. So we can able to see this is the cal NDVI TM ETM. So we have defined this function earlier here. So cal NDVI TM ETM. So where we apply the scaling factor so to this particular imagery, and we calculated the normalized difference vegetation index. And similarly, similar steps to be performed for Landsat 5.2. So the data availability from 1984 to 2013. And we're going to define a variable to access the Landsat 5 is L5 equals to earth engine dot image collection Landsat LT05 CO2 T1 L2, and we're going to select all the bands of Landsat 5 using dot select SRB dot star. So it's going to select all the bands of Landsat 5 imagery, and we're going to similarly apply the date filter function specific timeline from 1984 to 2013. So using dot filter date 1984 to 2013. Similar steps to be followed. For example, applying the filter based on a region of interest and the cloud cover lesser than 45% and WRS path of 39 and WRS row of 30. And we applying this function to this image for applying the scaling factor and calculating the normalized difference vegetation index. There is dot map cal NDVI TM ETM. So referring to this particular function I've mentioned here. So cal NDVI TM ETM. And similarly for Landsat 7 imagery. So for Landsat 7 LSC, that is SLC on that is from 1999 to 2003. And we're going to define a variable L7 on equals to earth engine dot image collection Landsat LE07 CO2 T1 L2. So this is a Landsat 7 imagery with SLC is on. And we're going to select all the bands using the similar step as we mentioned earlier, SRB dot star, and we're going to filter based on the specific timeline from 1999 to 2003. And based on study area, we're going to filter based on study area and the cloud cover lesser than 45, WRS path and WRS row, and we're going to apply the function dot map cal NDVI TM ETM. And in case of Landsat 7 SLC is off, that is with gap filling, we applied the focal filter, so in order to fill those gaps in this satellite imagery. So similar steps, variable L7 off is earth engine dot image collection Landsat LE07 CO2 T1 L2, and select all the bands, fix the time period from 2003 to 2024, and the area of interest, that is the study area, cloud cover lesser than 45, WRS path and WRS row 29 and 30. And we're going to apply this function. So in this function is different from the previous one. So where we applied the median focal filter, so you can able to see that we applied the median focal filter, and we applied this blend function in order to merge both the image together, that there is a gap fill image as well as the NDVI image together using the blend function. And last is the Landsat 8 imagery. So similar steps, we are accessing using variable L8 referring to Landsat 8 imagery, and similar steps, and we applying the function to calculate the We apply scaling factors and calculate the normalized difference vegetation index. And similarly for Landsat 9, variable L9 is Landsat 9, Earth engine image collection, Landsat LC09, CO2, T1, L2. So selecting all the bands of Landsat 9 imagery and suitable time range, and based on our region of interest, and selecting based on our filtering based on our region of interest, and cloud cover lesser than 45, and the WRS path in WRS row is 39 and 40. Last, we are applying the function to apply the scaling factor and the normalized difference vegetation calculation. So this function referring to this particular one here. So Landsat, that is cal NDVI OLI. And last, we're going to merge all this image together. So we're going to merge all the image collection and sort by the date. So to do that, we're going to mention a variable merged NDVI. So to merge all the Landsat series imageries together, we're going to mention a variable image merged NDVI. So we are referring to Landsat 4, Landsat 5, Landsat 7, 8 and 9. So we're going to mention a variable merged NDVI equals to L4.merge L5 and L.merge L7 on and .merge L7 off, and merge .merge function L8, and last is a merge L9. And we're going to sort by date using sort function system time start. So it's going to sort by date. And last, we're going to perform the time series analysis for our NDVI for over 40 years of NDVI for the study area. So this particular study area. So to do that, to visualize the time series plot of the NDVI for over 40 years, we're going to mention the print ui.chart.image.series, and we're going to refer the merged NDVI referring to this particular variable where we merged all the Landsat imageries together, and the area of interest here refers to our study region, and we're going to apply the statistical function that is Earth engine.reducer.mean function to acquire a mean NDVI image for each year, and the resolution I'm going to mention is 100, and the system time start. And next is we're going to set an additional options to this particular chart using set options, and the title I'm going to mention is 40 years of NDVI trends, and V axis the title is NDVI and the H axis is title is in year. So let us run this code and visualize the result here. So we're going to navigate to the top section here. I'm going to click this option called run, and let us visualize the result here, the 40 years of NDVI trend for the study area. So now here you can able to visualize the 40 years NDVI trend here, starting from 1985 to 2024. So you can able to see the NDVI value ranges from -0.5 to 1. So we're going to click this option to visualize this graph in details. And this is the NDVI trend for this study area. You can able to see the values here. So you can able to see the highs and high values of NDVI can be observed here, as well as the low value of also NDVI can also be observed in the study region, which is observed during February 2002. You can able to see that. So let me get back to Earth Engine. So the next step, we're going to visualize a few images. For example, so visualization of SLC-off gapping filling of Landsat 7 image. So let us add that image. So I'm going to mention map.add layer L7-off referring to the Landsat 7 with SLC is off, and we're going to mention dot filter date, and we're going to apply the filter date from 2005 to 2006, and we're going to mention the dot two band function to add all the images as a stacked. So we're going to mention dot two bands, and we're going to clip it based on our region of interest, that is area of interest, and that is our study area. And we're going to set the visualization to be the default visualization, and output as a SLC-off NDVI gap filled. And similarly, we're going to add another image, that is Landsat 9 image, and similarly I'm going to mention as map.add layer L9.filter date 2023 to 2024 dot two bands function. So it's going to stack all the image together, dot clip based on the area of interest and the default visualization parameter, and output the layer as L9 NDVI. And the last is we're going to export one of this image to our Google Drive. So for example, we're going to export the 2010 NDVI composite of 2010 imagery. So to export that, we're going to mention export our image dot derived, and image you're going to mention is merged NDVI dot filter date. I'm going to mention from 2010 to 2011, and dot two band function, and dot clip based on our study area, and we're going to mention as a float function. So we're going to export this image, and description I'm going to mention is the NDVI composite 2010, and the scale is 30 meters. And the next step is the coordinate reference system is we're going to mention as EPSG 4326, and the max pixel value we're going to mention is 1:10 power 13, and last is the region of interest, that is our study area of interest, and the folder I'm going to mention is NDVI analysis. So we're going to run this code and let us visualize the result here. I'm going to navigate to the layer section here, and I'm going to turn on this image called SLC-off NDVI gap fill. I'm going to turn this on here, and it is loading here. So the image got loaded up here. So we're going to navigate this option here, and I'm going to select one band as a grayscale, and you can select any image of your choice here. So we have this date 2005 February 26. So likewise you can select any of this date here. For example, I'm going to select during August, and I'm going to select the custom option to stretch 90%. And once you selected that, next step I'm going to click apply, and now we're going to visualize the result here. So I can able to see here all the white areas here, which indicates the high NDVI value regions, and all the darker areas, for example, which indicates the low NDVI. For example, this particular black area which indicates the water body. So you can able to see from this image here, and this is the water body, this is Snake River, and white area which indicates high NDVI value. Similarly, you can select any image of your choice here, that is suitable date. And next image, we're going to turn on the Landsat 9 NDVI, and we're going to navigate to this option called this option, and I'm going to select the band, and I'm going to select suitable timeline here. For example, I'm going to select August similarly, and the custom section I'm going to apply stretch 90%, and we're going to click apply, and you can able to view the result here. They're similar to the one above I have mentioned. So I can able to see all the white areas which indicates the high NDVI value, and the darker areas which indicates the low NDVI value, which is the water body here. So you can able to see the difference here. And this particular is 2000, I think in the year 2010, and the second image which refers to first image is 2005, and second image is 2023. You can able to see the difference here. This is difference 2003 versus 2023. So in the last step, we're going to export this image to a Google Drive. So we have the task section here, we have NDVI composite 2010. So we have specifically we're going to export the NDVI image of 2010 here. So you can able to see here 2010, and we have to export this NDVI image to a Google Drive using the, we're going to click this option called run, and a window pop up saying initiate image export NDVI composite 2010, and the coordinate reference system is EPSG 4326, and the spatial resolution is 30 meters, and we're going to export to a drive folders NDVI analysis. From the file name is NDVI composite 2010, and the file format is in GeoTIFF. So to export this image, you have to click this option called run, and I'm going to cancel this. So in this video I have shown you the 4-decadal NDVI analysis using Landsat image series in Google Earth Engine. So we have performed 40 years of NDVI analysis using Landsat series using Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like, and the code link will be given in the description section of this video. Thanks for watching.